I will try my best. It won't always happen. Sorry. Okay? Now, here we go. Today's lesson is going to be all about the concept of torque. This is a big deal. You probably want to jot this down. If you have Mr. Patterson for a class, this will be filed under the great biggie notes sort of thing, as he would call them. Quote, former President Joe Biden when he was in office as a vice president, either do something or go away. It's your choice. I don't care. But you're kind of irritating just sitting there doing nothing. Okay? Write it down. Type it up. Those are your two choices. That's the big deal. It's the big effing deal there, as Mr. Biden would say to Mr. Obama when they were in office. So, this is huge. I cannot understand this. Can't oversell it. It is a big deal. Torque is going to be when we're talking about tightening bolts down. This is what we're going to be discussing when we tighten bolts down properly. It is what we're going to use to describe that. I'm going to actually define it here in a jiffy. It's going to be a big deal because do you want your wheels coming off when on the highway? No. I don't. That kind of sucks. Do I want stuff on the engine to fall apart when I'm driving? No, not real fast. No. I would like them to stay where I put them. Thank you very much. Some things, for instance, the little nut on the can opener. It might annoy you that it backs off. The world will not end if your can opener falls apart. Okay? Oh, my can opener is kind of floppy. Oh, there, I fixed it. Okay. Not a critical piece of infrastructure. All right? I'm going on the highway. Why am I on three wheels? Well, because some idiot didn't tighten your lug nuts down and they came off. Whoops. This is going to be a huge concept. Also, when I was a kid, for some reason, no, not for some reason, because I had, I don't know, some pride or something like that. I don't know, whatever. I was always breaking nuts and bolts. I was always breaking them. And that's because I was constantly over-tightening the nuts. And then they would just snap off. And my dad would go, "What are you doing, idiot?" And I'd be like, "Well, I didn't want to come loose." He's like, "What is wrong with you?" And I'd say like, "Well, I don't know. I just didn't want to." In reality, it was like putting on a gun show, if you will. Now, okay? Somewhere between those two is the appropriate amount of, okay? When I first started teaching out here, like 4 or 5 years ago, whatever it was, first day I came into class, this kid goes, "Can you help me with these bolts?" And he's like over there sweating. And I'm like, wow, it must be really tight. I walk over and I barely push on it and move. I'm like, are you just messing with me, right? He's like, "I couldn't do it, groom." I'm like, okay, all right. I assume that people will be more like me. It's not true. Nowadays, it's more like, I guess it's tight. It's freaking hand tight. What do you mean it's tight? So this concept of torque is something we'll use from now until you're done with my class. 4 years from now? 8 more months, by God, and we're done with you. Okay, good. Cool, whatever. As soon as, until you're done with me, I will harp on this a lot. Okay? This will be how we rate how tight we get something. This is a big, big concept. Cool? Not a hard concept, though. Let me tell you a story. Back in the day, I was a fat kid, like a really chunky fat kid, like really fat. Now there was 5 of us fat kids in my grade school classes. Always, it was me, Ches, Chris, Derek, and Andy. Now Derek and Andy were really big, but the other 3 of us were pretty portly. Groom was always the tallest of the bunch, so even though I was a fat kid, I didn't stand out quite as bad because I was pretty tall at this point. Yes. Now Mr. Groom finally grew out of it, if you will, to some degree. It's still there. Groom covers it up. You're welcome. Okay? Now, I don't walk around showing off my little belly button ring because that would be just weird. When I went to teeter-totter, back in the day, my favorite playground piece of equipment, back when I was like in 2nd grade or 3rd grade or whatever, was the teeter-totter. Loved it. Okay? We can't really do it anymore because A, your fingers might get pinched, and B, the fat kid's feelings get hurt, apparently, I guess. I don't know. But whenever I wanted to teeter-totter with my buddies, here's Groom. I don't know. Actually, I was kind of pissed because my buddies couldn't teeter-totter with me because all my friends were skinny and short. And it would never do this because we could never balance. It always looked like this. Come on, Jimmy, teeter-totter with me. I can't, Jay, you're too fat. I weigh 35 pounds in the 3rd grade. Then eat something, Jimmy. All right, now, here's the deal. The fun of teeter-tottering is, in order for this to work, it needs to be properly balanced. Are you with me? It needs, because you push up, whee, You push up, wee. You put wee. So if it's me and Chaz, we could have some fun because we weigh about the same. We could go boink, boink, boink all day long. Keith and Jimmy could have fun because they were scrawny little kids all day long. You could put Keith, Jimmy, and a bunch of other people over here, and then maybe I could have some fun with them. Okay? Now, what was happening here is this. Mr. Groom has a certain amount of force. It's quite a bit of force. Jimmy has a puny little bit of force. Now, Jimmy, however, has quite a bit longer of a lever than I do. Mr. Groom's lever is kind of short. Nice. For us to balance out, torque actually, by definition, is this. It's equal to the force in a perpendicular direction times the length of the lever. Now, what do I mean perpendicular? Let me draw you a picture. Here is a bolt, a nut, or whatever. I don't really know. I can't tell just by looking at the end of it. Here is a wrench. Oh, it's an open-end wrench, Mr. Groom. Very good, very good. Nicely done. Well done. Nice. Now, when Groom pushes down thusly on the wrench, this is the maximum amount of force I can exert is pushing downwards like so, yes? If you had to push kind of like this, part of your force is pushing downwards, and part of it is pushing towards the nut, yes? The only part that's going to go towards getting the thing to move is the part that is perpendicular to the wrench, if you will. Now, right here, right now. Every time from now on, that's where you sit, right now. Now, when we do this, this is a, yeah, that won't last long either. So here's what's going to happen. Whenever you're pushing on something, take some notes on this, it's a big deal, as I was saying. Whenever you're pushing on something, it's only the perpendicular force that matters. Okay? Like the screw, my hand's in kind of a weird position. I can just barely push on the wrench. The wrench wants to go downwards this way. I can only kind of push that like this. Guess what? You push as hard as you want. Only the perpendicular part is what matters to move it. Those of you that are in like Algebra 2, a little bit of geometry action, you're doing sine and cosine. Have you done that? Little sin button on your calculator. What's that for, Groom? Turns out, there's an angle right here. What? That guy over there, friend, is the opposite side, yes? That side right there, that is why this is one way why we study trigonometry. Because you can push as hard as you want, bro. You're pushing on the hypotenuse, yes? But you're only getting the adjacent side amount of force. That's right. Now, what happens if I'm pushing this way on the wrench? Does the thing turn? No, you're an idiot. You're pushing the wrench onto the bolt. Like, get on there harder! I'm on there, bro. Why won't it turn? Because it must be perpendicular to get it to turn. It has to happen. Take it in the bank, sir. Every time. Now, when we do this, this is a big deal. So it must be the force that is perpendicular to the lever times the length of the lever arm. That is a big deal. Mechanically speaking, that's what it means. So, suppose that you and I, Kai, are going to be tightening this bolt. That is not a bolt, Groom. Fine, here's a bigger bolt. Mr. Groom cannot get it to move because Mr. Groom is using a wrench that is a whopping 1 foot long. And Mr. Groom is pushing on it with a force of, oh, I don't know, 100 pounds. Mr. Groom, oh, 1 foot. I wrote 1 inch, 1 foot. It would be really hard, by the way. It would be really hard to turn any bolt if you had a 1 inch long wrench, would it not? It'd be kind of hard to do. It'd be like, uh-oh, is that thing flickering? It's flickering up here. Hang on. Nice. Nice. It would be really hard to take, remember we talked about that a while back, one of the questions on the, what's that stupid game we play? What? Kahoot. On the Kahoot? Remember that one of the questions was the crow's foot? One of the responses was a stubby open-end wrench. Right? Could you turn it with that? Not very well. There's no lever. Now watch. Check this out. Mr. Groom, torque. What is the torque here? Well, check it out. It is wait for it, 100 pounds times 1 foot. Wait, that means it's 100 foot-pounds, we say. I want you to jot that down. Foot-pounds is one of the units of force that we'll measure torque in. It is a length, that is feet. It is a measure of force, pounds, foot-pounds. Seth, you might make a note of this. I think normal people say foot-pounds. Some people say pound-feet. Oh, no, it's not the different. Because remember, multiplication is commutative, yes? Flip-flop that order all day long. Makes no difference to us, okay? Now, I cannot budge this thing. This nut will not turn for Groom. Won't happen. Will not happen. So, guy comes over, says, Groom, I got you. I got you. Get the wrench here, whatever. Hey, it's the same wrench. Not quite, friend. And then wait for it, puts an 8-foot pipe on it. What? And then proceeds to push out here with a force of only 50 pounds. 8 feet long. What? Yes. So what is the torque here? Is 8 times 50 is 400 foot-pounds. I don't know if it moved, but it sure has a better chance of moving for Kai than it does for me on account of that's 4 times more torque than I was applying. Is there any reason I can't use a bigger lever? The only reason it's stopping you from using a bigger lever, sir, is how much room you have to move said lever. Yes? At some point, you're like, I could really use a longer handle. Bro, you can't get in there because there's not room for a longer handle. At which point, you're going to have to just man up, put some more force on it. It's one or the other. Are you with me? I can make one bigger. I can make them both bigger, I suppose, to a point. At some point, you're going to run out of spinach. Yes? There's not enough left in you. You don't have enough lead in your pencil. Now, as we're doing this is a huge concept. Oh my gosh, I cannot overstate this. Is that why that over here in the drawer we have, I don't know, this thing here called a breaker bar, which is fairly lengthy, versus this little pretty little half-inch drive, almost the same size socket. But how much more force could I apply with this one than the bottom one? How much more torque? Like double. Why? Because it's light, twice as long, yes? Yes, sure. Yeah, nice. Very easy to do. Now, is that why, Groom, when you said get the appropriate size tool for the job? Yeah, this one here for a big one. Now, the other day, this kid was taking off this itty little bolt. He goes and grabs. It was a half-inch drive socket, but it was a ratchet, but it was about this much longer. I'm like, what are you doing? He goes, I'm going to take that bolt off. I'm like, why are you using the biggest ratchet that's in the cabinet? I don't know either. What could happen very easily? Oh, snap. Oh, it broke, Groom. Shocking. Shocking, I say. And that's not shocking at all. We use the appropriate size. Hey, this one is like twice as long, so for the same amount of force, I'm going to get twice as much torque on it. Yeah? I think it's only 60%. I think you're wrong. Okay, whatever. So just be aware of that. It's going to be a lot more. Now, as we start to do these, it's not very hard to do. It's actually quite straightforward. Now, I will say this, in metric, because we will be working on foreign cars and even American cars since the 90s, pretty well mid-80s. I feel like I'm seeing someone drive in and it's weirding me out. I see a reflection in the car and I'm sorry, I just, squirrel! I don't know. All the stuff that we will work on from the late 80s, pretty much on, mid 80s on, will give you some of the measurements in metric. Even the American cars, yes. Now, will they still give you torque specs that are in foot-pounds too? Absolutely. But all of your Asian cars, all of your British car, European cars, British, all of your European cars will be in metric for show. Now, we still have the ability to convert them to metric too. But I want to show you this. In metric, the unit of force is called a Newton, which we abbreviate N. And the unit of length is a meter. There's a T in the wrong spot, dummy. Is a meter. And so newtons times meters are, wait for it, Newton meters. And you just say Newton meters. Now, this is what it'll say in the actual torque spec, Nm, Newton meters. Mr. Groom, what if I don't know which it is? Well, first of all, the programs that we use to get this information will give you both, Kenny, almost always. Almost always. But what if it doesn't, Groom? Here's a cute little thing. You go on the giggles and you go, I'm just going to show you. I'm just going to show you. Mr. Groom, I only have a measuring stick that gives me, a torque wrench rather, we'll talk about pretty soon. I only have one that reads in foot-pounds. But this thing said I needed to have 230, for instance, Newton meters to foot-pounds. You literally ask Siri. I bet you could even ask her. What are you doing over there? Are you typing this into Betsy? See if I'm right? You're checking me, aren't you? You're checking me, aren't you? Stop it. Hey, Siri, 230 foot-pound or Newton meters to foot-pounds. I don't know. I bet she'd do it for you. Hey, look at this. You click on it. Oh, look at that. It's 169 foot-pounds. What? Will it do it the other way? You know it will, because it's the 21st century. You can always go back and forth. Always, 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 always. Now, there is one more unit of this we could think about. What if I had a super tiny little nut or bolt? Here, I need to tore it down. Mr. Groom, my wrench is very small, little wrench here. It's only like 4 inches long. Well, that's interesting. And what if I push down with a force of, I don't know, 20 pounds? Well, that's going to be weird, Groom, because it's not in foot-pounds. It's 20 pounds times 4 inches. What does that come out to be? Well, it turns out it comes out to be 80 inch-pounds. That's right. And so for very, 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 very tiny amounts of torque, we will use the unit of inch-pounds. Okay? So how tight do I tighten this little itty-bitty bolt that goes into plastic? Probably inch-pounds. I'm just going to go on a limb and say that. Okay? Holding my wheel on my car, it's not inch-pounds. It's not inch-pounds. That's going to be foot-pounds. And it's going to be quite a few of them, like 100 of them or something. Okay. Here's a question. How many, let's see if we can convert this in our heads. How many inch-pounds in 1 foot-pound? Go, do it now. How many? Yes, yes. 12 inch-pounds, unsurprisingly, is equal to 1 foot-pound. How did he do that, Mr. Groom? Because it's 12 inches in a foot. I mean, duh, right? Nice. Wait, so if my car tire were to take 100 foot-pounds of torque, that's 1,200 inch-pounds? It is. Again, use the appropriate, this would be the appropriate measurement in that situation. Could you, is it possible, could you talk to me about how many tablespoons of water are in an Olympic-sized swimming pool? Yeah. You could. But a normal person would not measure it out by the tablespoon. A normal person would probably use gallons. I'm just saying, it's the more appropriate measurement. Okay? And so it's a bigger measurement. It makes it. Likewise, could you measure out how much baking powder you need for 1 batch of pancakes by the 5-gallon bucket? You could. It'd be 0.000002 of a 5-gallon bucket. It's weird, bro. Why don't you use a tablespoon or something? Okay? You're a weirdo. Okay? You could also use the dump truck amount too, right? Like how many dump trucks of baking powder does it take to make 1 batch of pancakes? 0.00. How long you got? 0.0000. Use the appropriate unit. Okay? We will use frequently foot-pounds and inch-pounds. Inch-pounds for the small stuff, foot-pounds for the big stuff. And then again, you will see, when we look stuff up, you will see it also labeled in Newton meters. Sometimes exclusively in Newton meters. I bring it up because I want you to see it's just a different unit, just like meters is a different unit than feet. Okay? Not surprising. Okay? Not surprising. Now, all right, cool. Now, here's a question. I'm screwing something down. Let's say I'm going to screw two pieces of metal together or something. Okay? Well, no, don't do it, for instance. Let's just show. Hey, here's an engine right here. Here's an engine. Oh, it's so good. Boy, it's facing the wrong way. Oh, yeah. I would like to put the part on top of here that goes on top. You can't really see much. I'm just going to bolt something on here. You with me? It's one of these guys. Are you exaggerating how heavy this is? No, it's like 80 pounds, maybe 90. It's pretty heavy. I'm going to set this guy on here like so. I would like to stay on. Okay. Now, how many bolts hold it on? Good question. I'll count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bolts hold that sucker on there. Screw. Is it going to experience quite a bit of force as those pistons are going up and down? Yeah. So when I put the bolt in and I tighten it down, eventually that bolt's going to quit turning. Are you with me? It's going to quit turning. It's not going to go in anymore. And you're like, what's it going to do? It's like you're carrying a baby or something. Who's this weirdo bringing her baby into the shop? Nice. You should have that happen every day in that case. All right, now, where was I going with that? What was I saying? Oh, I know. So as you're tightening that bolt down, eventually the bolt is going to quit going down. Are you with me? Because it's going to run out of thread at some point. Yes, it's going to get all the way in. And yet, I submit to you, I can make it. I can still make the head turn. What? Yes. Wait a minute. If you're making the head turn like this, what's happening, Mr. Groom? Because the bolt's not going to go in any deeper. What am I making happen? I could twist it off. You are not wrong. I'm not going to twist it that hard this time. You with me? I could do that. Yes? Oh, whoops. Sorry. I'm not going to do that. But, put that thing away. Pro tip. For using texticating, do it so the groom can't see you. Hey, what's going on? Here. Now, as I was saying, that's where I was going about that. Now, what is actually happening, friends, is I twist it, I'm actually stretching the bolt. Wait, you're stretching steel? Yeah, I am. You're an animal. You know it. Am I going to stretch it a lot? No, not a lot. If I stretch it a lot, that'd be kind of weird. Yes, you can grab, Kenny, a piece of like bubble gum and hold it in your teeth and kind of pull it out. And you're like, oh, that's fairly straightforward and easy to do. Yes. The weird thing about bubble gum, once you pull it out, it doesn't unstretch. Yes. Kind of like, oh, now I've got to stretch a piece of bubble gum. You take a piece of licorice and kind of like this, and it would kind of come back to you just a little bit when you pulled it out. Remember, I'm not pulling it out 6 feet. I'm going, It almost acts like a what? When you pull it out and it comes back. What's that? Like a spring, indeed. And that's exactly what's happening. When I twist these bolts down and I get them tight and then I keep going a little bit more, it actually is like a spring. When you stretch it, what are you doing? You're storing force in the thing, yes? When you let go, bam, it actually comes, yes? It can't come back because the metal is in the way. Are you with me? Like it literally cannot snap back because there's metal together here. Wait, so like two pieces of metal slammed together. You're screwing a bolt through there, and you're going, ah! You're holding a bunch of force together. What's that doing to these two pieces of metal? It's smashing together even tighter. We call that clamping force. Whenever we use a bolt and a nut, or just a bolt, whenever we tighten that down, what we are doing is we are applying what we call clamping force. So, when you tighten a bolt, nut, or screw, right? You are smashing, if you will, two surfaces together. In this class, it's going to be metal on metal. That's what we do here, right? That's what we do. We don't screw a lot of like
Mr. Groom, I was screwing a picture frame to the sheetrock. That's not what we do here. But it's the same principle, yes? You're taking and screwing something to the wall at home. It's the same thing. But here it's going to be two metal surfaces together, right? Wheel to hub, whatever it happens to be. All right, now, as you continue tightening the bolt, screw, whichever it is we're doing, stretches, applying clamping force, that's what the big kids call it, to hold the surfaces together. That's a big deal, clamping force. Okay? Now, this is I want you to understand it kind of thing. Are you with me? I am not going to probably use the word clamping force a whole lot after this little unit we're talking about. Okay? It will always be true though. Okay? When I'm tightening something down, I get to the end, I keep going, stretch it out. I am stretching it, I'm applying force in it that's doing that. It's like a spring. Okay? And it's smashing or clamping those two surfaces together. That's what's happening. What do you think? You say something? Like you're waving at me. Okay? If you can't read it, let me know. I swear it's American. It's English. I swear it is. I don't know. Maybe it doesn't look like it. Ancient hieroglyphics or something. That cool? Guys, that make sense? I got something there I'm missing? If you can't read it, let me know. Andrew! He's just back today. He took a forced vacation, if you will, because he had the problem. He had the problem for a couple of weeks. It's like some of you people did, been gone for a couple of weeks or 5 or whatever. Well, some of you have been screwing off, but a couple of you got to go away for a couple of weeks at a time. Yeah, same principle. I just missed the fellow. Thanks, guys. All right, now, the clamping force. Now, different things obviously need to be clamped harder, yes? We mentioned the wheels on my car. I want them clamped pretty hard, yes? Other things, not so much. A little plastic screw, doodads that hold the radio in, things of this nature don't need to clamp nearly as hard. Okay? Now, obviously, the manufacturer, Ford, Chevy, whoever, has decided that this is the appropriate amount of force that is needed to hold your wheel on. All right, cool. And so they will publish these statistics. They're called torque specs. And they say, hey, this is the amount of force that you need, the amount of torque you need to apply to this bolt so that it's clamped on with the appropriate amount of force. Okay, that's a big deal. Now, it may not shock you to know that sometimes you can stretch a spring too far, yes? What happens when you stretch a spring too far? It breaks. Well, before it breaks, what does it do? It deforms, yes. Now, I used to teach physics. This is one of the physics classes I love talking about. So I'm going to talk about it now. I don't get to teach physics anymore. I'm sorry. It's cool. So, when you stretch something, it turns out this is always true. This is the length that you stretch it. This is the amount of force that's applied. And it will always, hey, Mr. Groom, how much force does it take to not stretch it? 0. Duh. That's why this always goes through 0. Some of you that are in math, you're like, what does your y-intercept mean? It always means something. In this case, it means that it takes 0 force to stretch a bolt 0 inches or feet or whatever, yes? Not surprising, yes? Now, as it turns out, it will always follow a straight line. Hey, straight lines, don't they have slopes? They do. So it turns out that this formula is F equals K times X. That is always true. You should probably make a big deal about this. This is referred to as Hooke's law. It's for springs, but it's for anything that is spring-like. That is, it will snap back. Now, Mr. Grimm, how far is this? Like 1 mile? No, don't be ridiculous, loser. We're talking about tiny, like millimeters of distance. Are you with me? Tiny amount. You cannot stretch metal
out to a meter. That's ridiculous. It will break like in no time. We're talking a few millimeters. Are you with me? Like a half a millimeter, or like a tenth of a millimeter. Very, very small amounts. So don't get all weirded out about this, okay? Now, if this were an actual spring, can a spring stretch out some of them quite a ways and back? Sure, okay? But the bolts we're going to be talking about we're only going to be moving them just barely, just a few thousandths of an inch, if you will. Now, at some point, Ashton said, listen, you're going to deform them. And he's absolutely right. This is going to stop being, it's going to stop being linear. It's going to start coming off like this. And what's going to happen is, as the more you stretch it, oh, look, I don't need to apply as much force anymore, do I? All of a sudden, whoop, out she comes. Think about this with a piece of like bubble gum or licorice. You start pulling. What happens in the middle? You've seen it happen in the middle. It gets kind of thinner, doesn't it? And then it just goes a little easier, and then it snaps finally, right? At some point, that's what will happen. Now, when we're talking about bolts, we're talking about in this very small region down here is where we're fooling with. Are you with me? Because it's not moving very far. But the idea is the further I stretch it, because that's what we're doing, tighten down, we're stretching the bolt, we are applying more force this way. That's what we're talking about. That is huge. Got it? Question? No? Exciting. Now, at some point, what happens right here, by the way? Well, yeah, it breaks right there, yeah. Nice. We're not going to do that, please. Please, we're not doing that. So we're, again, talking about tiny, maybe 1,000th of an inch, 2,000ths of an inch, very tiny amounts of distance, okay? Tiny little amounts. Not millimeters, probably not even a full millimeter. That's a lot. Like you're like, a millimeter is tiny. Depends on what you're talking about. Hey, Mr. Groom, I started on my trip today. Oh, yeah, how far did you go? A millimeter. No, that's ridiculous. No, you're wrong. You're wrong. You're ridiculous. Mr. Groom, I stretched a piece of steel 1 millimeter. You are an animal, sir. That's a lot. Okay, that is a lot. So again, pay attention to that. If Jace told me he lost 10 pounds, first of all, I'm saying I'm not sure why you're doing that, because you look fine. I'm not sure why, but if he did, 10 pounds. Well, that's a lot of weight, because he didn't weigh that much. You go on the Biggest Loser show and they weigh 500, 600 pounds. I lost 10 pounds. Really? Can't tell. Okay? All right. Mr. Groom, could you lose, let's see, I can stand to lose 30 pounds. I'd look pretty good if I lost 30 pounds, didn't I? If I lost 30 pounds, like, yeah, all right, nice. Might even take the shirt off at the beach. Maybe not. But I can stand to lose 30 pounds. You're like, whoa, all right, yeah. The Groom, you'd notice, Groom, he would walk and pulling his pants up all the time. He wouldn't stay up anymore if he lost 30 pounds. If, I don't know. What is your name in the back? I can't remember. What? Jamie. Jamie lost 30 pounds. He's like, where'd he go? Where'd he go? I can't see him. He disappeared. I don't know, whatever. It would matter, because size really matters, yes? In terms of, like, if you're 400 pounds, you lost 30 pounds, whatever, I guess. If you weighed 100 pounds and you lost 30 pounds, holy crap, that's a lot, okay? So when we're talking about stretching here, we're talking about tiny, tiny distances of stretch. So kind of keep that in your mind. We think of, stretching things a long way. No. Not with our bolts. We're not doing that. Now, today I'm going to introduce you to something. This guy right here is a micrometer. You're going to spend quite a bit of time fooling with them later on. Quite a bit of time. But today I just want to introduce you to a couple of them and how they work. Now, recently we talked about thread springs, yes? This guy right here, check it out. I'm going to roll this thing in. Okay. When I get it back down here to 0, I turn it 1 full revolution. What? It went 25 thousandths of an inch. 1 revolution. 1 revolution is equal to, in this case, 25 thousandths of an inch. 25 thousandths. All right, so here's a question. How many threads per inch is that? How could I figure that out? Remember, 1 revolution is equal to 1 thread, right?
In other words, one revolution, I went around one time, I went up one thread. The distance apart would be one thread. Or one thread here. So what we're saying is this. I've got a screw inside of this guy, and these guys are 0.025 inches apart. How many threads would that be in 1 inch? Oh, wait, take a calculator. Ask Betsy. Get a calculator. Come on now. I don't know. I just work here. Oh, now you don't get your phone out? Get it out. Let's go. It's 1/40th? It's not 1. Oh, wait, what now? I want to see what's happening. Get your calculators out and play. All right? Take a wild stab. How many threads would that be? It's not 1/40. What'd you get? I don't know. You got the number 0.025, and you've got the number here, 1 inch. How many of these threads would there be in 1 inch? How would you? Yeah, 40. That's exactly. How did you do that, sir? What? 1 divided by 0.025, and you got 40 threads per inch. Boom. That is exactly right. That is how all micrometers are set up. Every single one of them that measures in English units, that is in inches, they will have a little screw inside of here that is 40 threads per inch. Wait, the one we did the other day was 18 threads per inch on our project, yes? So more than double that many threads per inch. Would you consider that fine threads? Yeah, and then some. Mr. Graham, I was just like ranking on this. Can I strip the threads out real easy? It's delicate, friends. It's delicate. Why are we going to measure with this, Mr. Graham? Well, it turns out that I went and I got some bolts. For instance, this one right. Oh no, where'd he go? Ah!
How about the ones over here?
Oh yeah, here they are. Ah, they're right here. I went and got some bolts, and I got this piece of metal that just happens to have some threads in it because we've been doing this. This is a 3/8 bolt, not 5/16. And I'm just like screwing it into the hole here like so. Now it stopped moving with my fingers. Yes? Can I still make it go farther? Yeah. What's going to happen to the length of this bolt the farther I go? It should stretch. Yes? Let's see if that's true. Let's just see if that's in fact true. Now, all micrometers work the same way. So this one though is a 1 to 2 inch micrometer. They all will go out 1 inch. So this one starts at 1 inch and goes out to a maximum of 2. This one is a 2 to 3. Starts at 2 inches, that's its 0, and then it can go out to a maximum of 3. You have 4 to 5, 5 to 6, 0 to 1, whatever you got. Okay? So this bolt happens to be, I think, just a skosh over 1 inch long. I was measuring it earlier. Yes, this one is. Da-da-da. This guy is 1.2. Nope. 1.216.5. Wait a minute. Are you telling me, Groom, that we can measure out to a 10,000th of an inch? Yeah, we sure can. With any accuracy? Well, yes and no. Could Groom do it accurately? I struggle with them, to be honest with you. I don't use them every day. I'm not great with them. My uncle, that's what he did for a living, with machine stuff. He was phenomenal with it. My father-in-law, great. Okay? Later on this year, when we get 10 inches down, you will be using them to do measurements. Some of you will be okay, some of you will be bad, some of you will be kind of, it really is something that you cannot master unless you practice much, okay? So, when we end up doing that later on, I will show you there's several different ways to measure some of these distances. There is an easier way for those of us who don't do it every day to get accurate measurements. And then there's this, which is really good. It has the potential to be good, but then I can screw it up pretty easy, couldn't it? And so, a person who knows what they're doing, that's a fairly accurate measurement there, right? So, that's pretty accurate. Now, what I'm going to do is I'm going to, where did I put that? Oh, it's over here. I wrote that down. Now, I am going to get that bolt back out. Now, I locked this down. I did not move it. I did not move it. Meaning that that measurement is not going to change. Okay? In theory. Unless I screw something up. I'm going to take this guy, I'm going to put it into here. I'm going to hold it in the vise so that it doesn't run out. I can't hang on to it otherwise. You with me? And I'm just going to put a wrench on it and turn it. I'm going to see what happens. Now, I just went with a 3/8 ratchet. Nothing special, nothing real long. Of course, I could have gone bigger. That's not really the point. Oh. Oh, is it going to break? God, I hope not. All right, now. Well, you really stretched that sucker, didn't you? You showed him, didn't you, groom? Now, I'm going to try to slip this back on there. Dude, it won't go on. It won't go on because you stretched it, groom. Now, interestingly enough, if I loosen it up and open it just a skosh, open it, I said. Groom, for presentation purposes, it would be better if this actually slipped right on real fast. And then the kids would be like, oh, whoa, groom, that's cool. But when you dinkle fart around it for 15 minutes, you kind of lose the sales procedure. I'm going to sit down. This is what I said about the appropriate person using it. It's easier to sell the bit if the appropriate person's using it. Come on, Jay, you can do it, bud. All right. Oh, hey, look at that. What do you know? 1.2187. 1.2187. Mr. Groom, you telling me you stretched it 2.2 thousandths of an inch. That's right. That's right. Or if you prefer, 1.0022. That's right. Now, how much force did it take? I don't know, quite a bit. Now, it's possible, well, it is possible, we're not going to do the math on it, but it is very possible to figure out how much force that took to do that. It's very possible. We're not going to, we don't need to for the purposes of this class. Are you with me? Now, could I get another wrench, a bigger wrench, and turn it harder? Stretch it more. Absolutely. At some point, you said I would deform it, yes? Ah, nice. And as a result, would I get the same amount of, would I get the same clamping force the next time I used it? Probably not, and you're absolutely right, sir. Spoken like a true engineer. Here's the thing. If I stretch that bolt and I deform it, is it ever going to go back to where it was before? No. So the next time I try to put the same amount of force on it, what's going to happen? It's not going to apply the same amount of clamping force again, is it? So guess what? I could have a problem. I'm going to keep using tires so it's easy to visualize. You with me? My tire could literally fall off on the highway because it wouldn't be putting as much force on there that it would need to have. Okay? Now, I keep saying that because it's easy to visualize. But the bolts to hold this engine piece together, these older designs, you could reuse the bolts. The bolts hold this on. The newer ones, since the 80s, they've been using a different style. They've been meant to stretch an appropriate amount and then stop. When you take them out, throw them away and get a new pair. Well, but why? Because just what this fellow here said. He said, no, listen, once they've stretched, they get deformed, and they will no longer provide the exact same clamping force again. So you pitch it, okay? Now, something to think about. Now, but Mr. Groom, what about this little bolt here that you used? Did you damage it beyond? No, it's fine. What are you going to put together this with? I don't know, my IKEA furniture. It doesn't matter, okay? Putting the kid's wagon together. Yeah, whatever. If he falls and breaks his nose open, it's going to be cute. It's a nice, sexy scar. It'll be fine. Whatever, okay? Lots of things. It's fine. Inside of my car, when my engine's turning over like 8,000 revolutions per minute, like in a NASCAR race, that's a big deal. That's a huge deal. You get on the highway, you mash down. I don't want my engine to come flying apart because somebody reused a bolt that was deformed. That'd be a problem. Okay, it might die. Okay, so we're not going to do that. What I have here is a bolt. This is a bolt from an engine. Basically the bolt I was pointing to, but not the same bolt. Are you with me? It's from a different engine. You'll notice that it has a spot where it's necked down and then it gets bigger on the end. That's a big deal because from here to here, this is down to a specific diameter. This is made so when it stretches, it provides an exact, precise amount of clamping force. But once it's been used once, no bueno. We toss it and we go from there. pass that around if you want. Notice how different it is than our other bolts to look at. Okay? Again, this is a very common thing. As you stretch a bolt, it can permanently deform, and if it does, it will not produce the same clamping force again. It can't. It physically cannot do that. Okay? Again, it does not mean that every time you tighten a bolt, you will stretch it beyond this point. Are you with me? A lot of times I'm just putting a wheel on the kids' wagon. I keep using that because it's very obvious. I don't need to tighten it very tight. All right, go play, kid. There you go. That bolt will never be stretched tight enough that I'm ever going to deform that. The bolts inside of an engine, very much so. Very much so. Especially the more high performance the engine is, I want to use new bolts every time. Okay? Because when I hammer down and I'm really putting the onions to it, I do not want to blow into a gazillion pieces. Okay? I just rather that didn't happen to me. Okay? Yeah. Okay? It will never produce the same clamping force again. That is a huge, huge, huge concept. Okay? Now, I'm going to show a quick video here. Back in the 80s, they came up with this new terminology. The terminology is new, but Ashton just told us what it is a few minutes ago. It's what is called torque to yield bolts. Okay? That is, you will torque them until they stretch a desired amount. Now again, that's back to this graph, F and X. If I stretch it to this much, I know it will produce that much force. Are you with me? Every single stinking time. But in doing that, you will have stretched the bolt. And so what they started doing was, back in the 80s, they said, hey, this is a better way of doing things. Okay? It's a better way of doing things because, well, here's an example of it. The other day when you were putting your threads in, some of you had to redo your threads, yes? Remember how hard it was to start the bolt? You're like, it doesn't want to go in very good, Groom. Oh, that's because you didn't have very good threads, maybe, okay? But what if I had crap on the bolt threads? So I had some rust on them, there was some dirt in the threads, and I started, gosh, it takes a lot of force to overcome the rust, yes? Does that make sense? I really twisted hard with the wrench to get past that. Well, that's torque, isn't it? You're putting force on the wrench, yes? You're applying torque there. So all I said was, listen, I want to take and I want to a certain amount of torque. If there's a bunch of crap in the threads, why, that's taking some of that torque and it's not clamping the wheel on, it's simply trying to get it to move down the thread. What they discovered is this. If instead of doing it that way, they get it down and then they turn the bolt another amount of turns, like say a quarter of a turn or a half a turn. Okay? If I turn it 90 degrees and I know what the thread pitch is, do I know how far the bolt stretched? I absolutely do, don't I? Okay, because I know how far apart those are. I know how much it's going to stretch, right? Because thread pitch, right, we know the distance between the threads. If I turn it a quarter of a turn, I'm going to turn it a quarter of a thread distance. That means it stretched that far. Then I could go to a chart like this. I don't have to. The engineers did it for me. Are you with me? And they said, this is how much force that I want to predict. So I need to stretch it that far. And to do that, I need to turn it a certain distance to make that happen. Okay? And it's a lot more of an exact clamping force to do that than it is simply by how much force you put on. Okay, it's a better way of doing it. So before I do that, I want to show you one more tool you're going to learn. Okay, I'm going to demonstrate over here, and you're going to see it. I'll pass it around as well. Okay, we'll be using this tool in our entire engine build, and then also when we work on cars later on, every fastener will have a torque set. Every fastener needs to be tightened to a certain amount. Okay, so right here are a couple of examples of them. Here's a couple of examples of them, and then I've got another one over here I'll show you in a minute. I'm going
going to use this big one for right now for demonstration purposes. Okay? This is referred to as a torque wrench. You should probably jot it down. It looks like a ratchet, Groom. That's because it's like a ratchet. You put a socket on. Could I put a crow's foot on it? Absolutely I could. Or I could put a socket on. Okay? It's a torque wrench. Wait. So it's calibrated to know how much torque you use when you're tightening it down? Yeah, it is. How does it do it? Well, there's two kinds. This one, God, kids don't listen to me. It just pisses me off. This one has a spring inside. There's a spring that pushes up, up onto this, and there's a little the word I'm looking for. There's a little ball inside of here, and it's on a little catch mechanism. When I turn it this way, at some point I will overcome that, and you'll hear it go snap, snap, snap. That is when you have reached the appropriate torque spec. And then you go, I should probably stop now. Cool. The nice thing about a spring-loaded one is that the batteries never wear out. I kind of really like that. I reach in the drawer, hey, it works. I have an electric one I'm going to show you in a minute. Guess what happens when you don't use it? Oh, I don't need it today. Oh, and the batteries are dead. Then you got to go take them out of here. Take them out of everything you own. Where's the day? I need some more double A's. Where are they? Because, well, I like these style a lot because this style just freaking works. Some of them have this style knob on the side here. You turn this little knob, that puts tension on the spring inside of here. Some of them have a deal where you turn the bottom handle. It's the same premise, it's a different setup. You get these guys, not the Snap-on one. You get this kind, the handle, turning handle part, really cheap, 25, 30 bucks, right? And they do good enough for what most people do, okay? This one was a lot of money. That's Snap-on. Now, I'm going to pass this around for you to look at. What you do is right here on the side, it has a little dial indicator deal here. You turn this knob, and you can read off what the actual torque is. Down here on the bottom, it has a Newton meters to foot-pound conversion because this came out before. Hey Siri, what is 100 foot-pounds in Newton meters or what have you? Yes, back in the day. Okay? Or maybe the book only gave it to you in Newton meters or what, I don't know, whatever. It's a nice, easy way of converting it. Okay? When you get it set appropriately, you flip this guy over the top, and you're ready to go to work. It locks it in place so it doesn't turn when you're working. That's kind of annoying. When you put these away, it is important on the spring-loaded one, always put it back to 0. That releases the tension on the spring. If you leave a spring tensioned all the time, it's going to change its length, and so you will no longer give an accurate representation. We tested this a couple years ago. This one reads about, it actually gets about 10% higher than it should. Okay, so if I want 100, it's going to give me about 110. Not the end of the world in the grand scheme of things. Okay, I'm not going to cry about that. Okay, may pass this around, Roman. Here, wake up. Or don't, you know, whatever. Smash the donut, but anyway, smash the donut. This is the 3/8 version of it. It's the same thing, obviously, just 3/8. I'm going to go tighten this nut down again with this guy here so that you can listen and hear it click, okay? Same premise, obviously, just a slightly different version of it. I'm going to go 30 foot-pounds just for fun. And where'd I put my bolt? Where's my little piece? Oh, it's right here. There's my little piece of metal. Again, all I'm doing is tightening it down, so listen carefully. Oh, I heard it! When you hear that, stop. Oh, I did it. I'm going to keep going. No, you're silly. You will break it. Okay? This gave you the appropriate torque, in this case, 30 foot-pounds. Stop what you're doing. Okay? Now, over here I also have our electric one of them. We have quite a few of these. I like them. I do. I don't know that I would ever purchase one for myself unless I was building engines all day long. I just don't think I would. Okay? Now, it's kind of expensive. The little spring deal works just hunky dory. Okay? I don't know. Turn on. You can select the U button and put it in different units. Right now it is in inch pounds. Now it's in Newton meters. Now it's in foot pounds. All right. You can raise the number of foot pounds, or you can decrease them. Now I'm gonna put it on 30 again. Okay. I'll pass it around in a second. But listen to this one.
Some of them will vibrate your hand like the fishing game. Ooh, I got a fish. I got a big one. Ooh, yeah, nice. This kind does not have a spring inside. It has what's called a strain gauge. So as you're pushing this down, this handle here, it recognizes how much strain you're putting on. It's a gauge. I don't really get how it works. It can't go bad, but it needs power to operate. Okay? So they work or they don't work. Okay? So that's what's nice about them. They are very accurate. The bad thing is batteries go down. You don't use them. What are you gonna do? And they're expensive. All right, compared to the other. When you're using one of these, your hand goes here. Classic mistake is people try to get both hands on it, and then you end up changing the adjustment here. And then you just keep going until it snaps off. You're like, what happened? Well, you raised the adjustment up higher, so you just kept going and it never beat because you never got to what you set it to on accident. Another classic mistake is people get their hand on the cap. This is the end of the battery connection. When you do this, sometimes it'll make the battery lose connection and the thing shuts off. Uh-oh, when's it going to beep? It's not. You are going to beep when you smash your hand when you break the bolt off. And then you're going to play beep, 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 beep for half an hour because you're pissed. Okay? Been there, done that. Okay? I don't like it. So hand goes here. This is where it's meant to be held from so it gets the appropriate amount of strain to measure as it's doing it. Okay? Pass this guy around. Don't drop him. It's expensive. You're replaceable as that. The torque wrench isn't. Okay. Now, on our projects, I will allow you to use both of them. I will show you where I store these things later on. Where's that one coming in? Coming in? Is it coming? Oh, there you go. Pass that up. There you go. Cool. 45. Oh yeah, we got time. I'm gonna show the video now. Now, as I said in the 80s, they came out with this newer style, which is called torque yield. The way they knew how far they stretched it is they kept track of how many degrees extra rotation they did. So 90 degrees extra, say 60, 180, whatever it happens to be. Obviously, 360 degrees of rotation will give you one full thread pitch of stretch. Yes, we're not gonna be doing that. We're gonna do 60, which would be 1/6 of it. We do 90 degrees, which would be a quarter of it, so on and so forth. Okay? If we're doing those at some point, the torque spec will tell you this is how far you should go. You should go an extra quarter turn or what have you. Now, the reason I like to show this video, it's very cool. It's obviously 1980s vintage video quality, so whatever, get over yourself. But what's really nice about it is it allows us to see they did a nice job of illustrating what's going on there. So I'm going to show that real quick. Auto 1. Torque angle. Here it is, baby. I'm going to speed it up just a hair. Make sure we get done. Come on. Oh, shoot. Damn it. Okay, wait, stop. I'm going to play it on this computer because I forgot. To use the computer speakers, I can't do wireless. I have to do this. Hang on. Just take a second. We got this. Disconnect. Connect. YouTube. We on yet? Come on, baby. There we go. Cool. And history, and bam. Here we go. By the way, yes, I pointed the camera at the screen and videoed it on the VCR. Belongs to Buick. There's my lamp in the background.
This is a torque angle meter being used to tighten cylinder head bolts. The procedure involves measuring two of the elements involved in tightening fasteners. Those elements are torque, the turning or twisting force applied to tighten the fastener, and angle, the number of degrees the fastener is turned. The torque angle meter is an electronic measuring device that provides accurate readouts of fastener torque and rotation angle. Today, we'll show how the torque angle meter is used, and perhaps more important, we'll explain why it is used. increasingly important role played by engine fasteners. That's right. Those crucial nuts and bolts that we probably take for granted more than any other parts we use. One of the principal goals in current automotive engineering is to achieve maximum performance from economical small displacement engines. To meet this goal, engines are being redesigned for less weight, increased power, and more efficient use of fuel. At the same time, quality and durability expectations are higher, so engines are required to last longer and be more reliable. To achieve the desired combination of power, lightweight, and durability, small engines must be designed and assembled with extreme attention to detail. The Quad 4, the 3800, and the 3300 are all new precision engines, specifically designed to incorporate these qualities. But refinements are not limited to new engines. In fact, in recent years, every engine used by Buick has had major design changes to improve performance. Increasing the power and precision of engines puts greater demands on the fasteners used to assemble them. Let's consider why. Fasteners in all automotive engines are subject to many stresses: vibration, heat expansion, internal pressures, and corrosive gases are all natural byproducts of internal combustion. Fasteners have to be able to withstand these forces and hold components together tightly enough to maintain combustion seals and prevent leakage.